So, welcome to this year's AArch64 performance talk. Um, the structures for my slides are going to be all similar. So at the bottom right, you'll see a number in the cloud. That's the GC release we think we can land the changes in. And all of these slides are a different patch series that someone in the team is working on. So the first couple of slides are addressing regressions. In GC15, there was an improvement done in if conversion. But unfortunately, the default if conversion cost model does not exist. And so GCC will happily if convert these quite long chains now. And because of this, we've gotten very big double-digit regressions in a lot of workloads like ZSTD and stuff like that. And so the first thing is to try to teach the cost model about misprediction penalties, instruction chain lengths, and stuff like that to block if conversion when it's not beneficial. And to balance that out, we have people who say that, well, you can never tell me, we can tell beforehand that the branch is going to be unpredictable. How can we tell the compiler this? So that you do always generate a C cell for me, or a if converted statement. So GC has a built-in expect with probability. And so we figured we can use this and a weight. So in this case, we'll tell it each branch is 50-50. And in that case, we will let through the if conversion regardless of whether we think it's going to be profitable or not, since the user said it would be. This also allows us to use PGO information because it uses the same kind of information to determine whether we want the C cell or not. So next thing we want to do is start unrolling small loops by default. At the moment, these simple as defined like loops, they don't get unrolled at all, but they can benefit from some unrolling. Typically, what you want to do with unrolling as well is do optimization that the CPU couldn't do on its own. So, for instance, break accumulators, form load store pairs, etc. However, GCC's default quote stupid unroller, which is what the path is called, is quite stupid. It essentially just copy pastes the code. That means that if you unroll by a large amount, you have to go through a very long sequence of comparing branches before you even get to the unroll code. So usually unrolling just makes your code slower. So we've been trying to fix this. Modern CPUs don't have much of an issue with indirect branches. So for instance, we tried using a dispatch table. Since we can't statically tell the size of each block, we can just use arithmetic to address it. Clang also, when it does unrolling, will rewrite the pointer plus offset changes into just pointer shifts. This makes the code quite a lot more dense, and in fact, you gain a lot by it. Unfortunately, the code became so dense that you breach branch density rules. So then you actually have to sprinkle some knobs in there to actually recover the performance. So that approach also doesn't seem to quite work well. So what we're trying now is to do like what the vectorizer does. And so you have a main loop that's unrolled, and then you go down through different epilogues. That allows you to get through the main loop quicker, but then to get to your origin scalar code, it's only 1 or 2 branches, instead of at the moment 16 for the maximum case. We're doing quite a lot of cost modeling changes this year. So to aid in our experimentation, we've added max factorization, which is essentially almost the same thing as disabling the cost model, except it doesn't disable inner vector cost modeling. So the F no vector cost model will just pick the first vector mode that's possible. This one will still cost between the different vector modes, but tell you vectorization is always profitable. This allows us to test different loops. We've also promoted the hidden AArch64 variable, AArch64 autovec preference, into a supported parameter now. Here you can tell it I want advanced SIMD only, or SV only, or advanced D first, or SV first, etc. So it allows you to play with what factorization you want from it. And we've adapted the vectorizer to put out statistics. So for instance, if you're compiling over very large suites, you can now get a JSON file output saying, okay, I didn't vectorize this because of these reasons, or we could have vectorized this loop, but the cost model said no, etc. It allows you to analyze code a lot better. We are also changing our cost model, so we take into account throughput at the moment, but only for very limited cases, like predicates. But we also need to take into account general throughput limitations, like, for instance, shifts are generally lower throughputs than general ALU operations, etc. This becomes more important as the vectorizer becomes more capable of generating code with control flow in it. And typically, those control flow blocks introduce a bottleneck. And so we have to pick correctly which ISA to use if you need to unroll, etc. This feeds into early break. If you may or may not have noticed, we're doing quite a lot of work on vectorizing control flow. Unfortunately, the cost model today isn't really set up for this. The vectorized cost model expects one giant basic block, and that's the only thing that executes. It doesn't know about jumping to different basic blocks, etc. Our friends at NVIDIA are also working on being able to feed the compiler a cost model as a JSON. This is mostly for experimentation, not something we expect end users to use or want to use, but it allows you to just be able to quickly tune a CPU or a workload without having to recompile the compiler constantly to test out the cost modeling. And they're also working on dispatch-based scheduling. X86 has had this for a while, so we've implemented these hooks now. Now it comes to missing features. So one of the big issues that we have in GC today is it forces you to pick between two things. Either you get CSCing of constants, or you get constant anchors. If you pick CSC, that means that you get the code at the top here, where these two constants, you have to constantly rematerialize the addresses. And so for stuff like, let's say, OpenSSL, where they have a lot of prime numbers and stuff like that, the first part of the loop is just constant address rematerialization, even though the constants are sequential to each other. At the moment, the workaround most people use is putting an airline as a volatile there to force it to keep them together, but this then blocks all the optimization. So it's not ideal. So we're trying to work out if we can get both CSC and constant anchors to work together. Zero extension. At the moment, GCC doesn't realize that if you sign extend a zero extended value, that's also a zero extend. Now, why is this important? Zero extends are a lot cheaper. Zero extends, you can typically just move a value into a vector of zeros. So for instance, at the first part here, we zero extend it. We replace the actual zero extend instruction with a permute. It's a lot quicker. And then from that point, it thinks it's sign extended. It thinks it has to sign extend. But we can use Ranger to figure out that the top bits are zero, and then just extend the sign extend range. And then we can transform it into table lookups. So instead of like having to have a sequence of instructions to zero extend from say a byte to a long, you can simply have a permute that just shifts the values in the right zero location. This not only makes the dependency chain shorter, but it also makes all the instructions independent. So like here, all the TBLs will execute in parallel. Versus here, you have a two instruction chain for every sequence. After discussing this with Richie back and forth, he did not want a new opt-tab for this. So instead, we're opting that if you remove your zero extend opt-tab, you will get the TBLs by default.
Is a lot of the work needed here actually architecture independent, or is it really back-end work?
So a lot of the work needed here is, what happens is that in the vectorizer you have these patterns that come in, and it tries to do narrowing. And when it does this narrowing, it inserts intermediate cast. So it kind of causes the problem on itself, because on the C level, it's just moving from one data type to one larger one.
Sure. Yeah.
And so the idea is to undo this work that the vectorizer has done when beneficial.
Okay.
And then we will model these as permutes. The reason for modeling these as permutes in the vectorizer is that because, for instance, if you have a loaded permute and you then zero extend, you can mix the permute of the load with the zero extend. So here, for instance, we have a two-lane load and permute, and then we do the zero extend. All of this is unneeded code, because we can then instead do a linear load, and then move the shuffling and the zero extend permutes together.
Right.
Unfortunately, at the moment, we force these group loads quite early. We don't get a chance to optimize them at all.
Right. Yeah, I'm asking because for power, of course, for me, of course, We have lots of unnecessary zero extents as well, and signed extents, by the way.
Yeah.
It's completely unnecessary. Stuff that you know that you should know that the value is already sign extended. It
Yeah.
still generates a sign extend instruction for it. Yeah, whatever.
Yeah, so yeah.
But I think that generic code should be able to handle a lot of the. Yeah.
Yeah, so like I said, in C itself, the sign extents don't exist. It's the vectorizer creating it.
Right.
Well, like you said, you have a value, you're casting it to something signed, but in between you have a unsigned cast.
Right.
So that means that the outer signed cast doesn't matter.
Right.
So
Yeah, we see a lot of it for pro-local functions where to mold the parameters into correct format. But the ABI already says that stuff is past sign extended anyway. So why does the generic code put an extra sign extend on it? It's yeah. Oh well, thank you.
Then we want to improve the complex number support path. Today, GCC supports vectorizing operations that exist on complex numbers. So let's say complex multiplication with rotation, complex addition with one argument rotated, etc. In AArch64, these are implemented by using two instructions on the same values with a different rotation. So for instance, this FCMLA instruction will do half the operation, then you need another one with, for instance, 90 to do the second part. However, these operations themselves are valid semantically. They just don't have any definition on a complex number. So instead of looking at complex operations, we'll extend it to look more at the data flow. And so this allows us to recognize these kinds of instructions on computation, which at the moment today we have to de-interleave, use FMLA, and then re-interleave. We can then just do linear loads. This happens quite often in a lot of scientific code. One of the other options is that we want to be able to use mask loads instead of having group loads. So what I mean is here, for instance, because you're loading every R bit, so it skips every element inside the original structure, we have to do a load lanes. So that means that we load here two registers, de-interleave them, but then never use the second one. This is, of course, wasteful, and it also means that then we have to zero extend these values independently. If we were to have used a linear load with a mask, and you mask off every even element, then we could have done a widening load. So this code becomes a lot simpler and a lot more efficient. So the work is to kind of relax the vectorizer here to say if you have a stride that you can express with a mask, use the mask instead of a group load. So as we keep going on curly break, in GCC 15, you could not vectorize a loop with the VLA that needed peeling for alignment because we couldn't peel it. Particularly for VLA, you don't know how long you're going to peel. And if you have, let's say, a vector length of 2048 bits, and your data type is byte, you'll end up with a prolog loop that's so long that you might as well not vectorize. So for GCC 16, instead, we added support for peeling using mask loads. So what we have is the first iteration, we create a special mask that calculates the amount you wanted to peel, masks off the elements, and then let you iterate. After that first iteration, you then continue with an align pointer. So that's what this computation here at the start is doing. Sorry? No. It's only for a single array at a time. Now, that's not entirely true. We did also add mutual peeling for alignment. So it's able to do it if the arrays are mutually are aligned by the same value. But if they're misaligned by different values, then it can't. You only get a version in check. Right, so that's the other work we added. Like for instance here, A and B, if they are misaligned by the same amount, you can peel them mutually until you have a vector alignment and keep going. VLA makes it a bit difficult because again, you don't know the vector length, and you need to be sure that if you're relying on alignment, that a single load cannot cross your page boundary. So let's say you've unrolled your inner loop, so then you're loading values at a time of, say, maybe 16K, and your page size is 4K. You can never align this. So that's why we have a page size check in the beginning compared against what we know is the maximum amount you're going to load in an iteration. And the user can control this with a parameter. It defaults the page size to 4K, but if you have a 64K system, you have to change the default value.
If you have hard-coded page sizes there, does this mean this is not compatible with MTE?
Yes. That's one of the big discussions that we have is what do we do with MTE? With MTE, as soon as we increase the alignment above 128 bits, it kind of won't work. Now, for MTE systems, we would use first faulting loads. So these are loads that you have what's called a first faulting register, and they accumulate the fault as you keep doing loads. So let's say your first load didn't cross a page boundary. Your second load can read only 3 elements before it hits a page boundary. You will trigger a fault, and you will get a mask saying you can do only 3 loads at that iteration. And so that's how it handles mutually misaligned elements, and also should be compatible with MTE. The implementation itself, we thought we could get it done by UC16, but it has a lot of complications. In particular, in Gimple, the first faulting register is not modeled. And so we have issues like what if you're vectorizing an inner loop, and the outer loop itself is using first faulting loads, or you have intrinsic code, and in between the set and the read, you had some code that accidentally got vectorized, or inlined and then vectorized, etc. So we hit an issue where we don't know if it's safe that we could factorize. So instead of, what we're doing at the moment is doing a bit of a data flow analysis before you start factorization to walk through the vusers chain to figure out, did any of these instructions here use the first faulting loads? And if so, did they actually read the register? And only then can we continue to factorize. There's also a bit of a requirement that you can get a unnecessary fault. The MMU can essentially say, hey, I'm going to give you a fault to give me a chance to go prefetch data, but you're not done yet. So you have to be able to distinguish between an actual fault and a false fault, because in a false fault, you have to restart the loop. You also want to avoid needing the result of the first faulting loads if no fault was taken, because otherwise this data dependency will force an order in the CPU pipelines. So you don't want to use this predicate if you don't have to. So that's why the vectorizer will kind of version the code, and it will need to duplicate code a bit. One to avoid the predicate, and the other one to restart the loop without doing any work if you take a false fault. But I have some more of this in the vectorizer talk. Vectorizer buff. Secondly is dealing with pragma unroll. So because we are able to vectorize a lot more code now, we realize that there's code that's been decorated with this pragma unroll that people never really expected to be vectorized. And what ends up happening is we vectorize the code, and we may have unrolled it, and then the RTL unroll just happily goes and stamps 16 copies again, which is not very useful because you just get a very large code block. So instead, we've taught the vectorizer to do the unrolling within it. So let's say in this loop, for example, you say, I want 8 times unrolling. The vectorizer will use this to seed essentially the vectorization factor. So for integers here, because every vector does 4 integers, you get 2 times unrolling. And then it clears the unroll flag and sets it to 0, which lets the RTL cost model determine whether you want to unroll further. So it doesn't prevent further unrolling, but at least it doesn't make it as egregious as before. This has other benefits, like for instance, in this case, I'm doing a reduction. Because the vectorizer did the unrolling, it can break the reduction chain. So the adds will happen in parallel, and then only after vectorization do we then accumulate and reduce. So it increases your throughput, which is essentially the goal for unrolling here. Then we are looking at how to make the early break code more efficient. So one of the issues we have is that, for instance, if you have to unroll and do multiple comparison, at the moment we have to reduce the results with an OR. This is nice, but essentially it makes your entire chain sequential. You have to do all this reduction before you can actually compare and branch. AArch64 has this instruction add half and narrowing. So it adds the instruction, it shifts down the high half, and then it narrows it to a small type. This is useful for us because we can remove the OR here, and the compression steps become simpler. So we replace the OR and the UMax with the AArch64. It gives us a 64-bit representation where we can test to see if any bits are set or if no bits are set. So this increases the throughput for these kind of loops by like 20%. When we originally created early break code, we decided that, okay, we will vectorize any induction value because if you take an early exit, you have to go to scalar code to replay your side effects in the right order. This is particularly if you don't have any masking support, etc. What we did at the time was, because the vectorizer knows how to vectorize code, we told it, this is an induction, you have to deal with it. But you end up creating a vector induction alongside your scalar induction. This is made worse by IVOps, because IVOps, if it sees a loop with a known iteration count, will add a downwards counting IV as well. And it expects, sorry, IV canon. And it expects IVOp later on to remove this, the duplicate IV. It just gives IVOps more freedom to pick between the upwards and downwards counting IV. So we ended up generating 3 IVs, 1 scalar, 2 vectors, 1 counting up, 1 counting down, and then IVOps doesn't understand the vector invariance, so it just gives up and goes, and just leaves them there. So the idea is that we now teach the vectorizer to vectorize code as scalar. So it will generate a new scalar induction instead. So you go from the first loop into the second one, dropping all the unnecessary vector inductions along the way. At the moment, I said, anytime you take an early exit, you have to go to the scalar code. This is not very efficient, especially on longer vector lengths, because your element might be, for instance, at the very last entry of the array, but then you will redo everything to get to that last element. So instead, we're extending the vectorizer to not require the scalar loop. The first case is obvious. The value you're returning is completely invariant. Doesn't matter, it doesn't rely on your IV or any load stores or whatever. So in this case, we can simply tell the vectorizer you don't need the scalar code, and the code it generates is already correct. So that's what you see here on the left. So it just moves 0 or 1 depending on if it finds the value or not. Second part is a bit more difficult. That's, for instance, if you're actually returning the induction value. SVE has these instructions where you can partition the mask and then count the number of bits active. So in this case, the break A will set all values in the mask to true up to before the first element that was true in the compare. So it essentially masks off the first parts in the compare. And then we ask it how many elements were active, and you add that to your current scalar IV. So return I simply becomes these 2 instructions. Then you have, okay, what if you want to return an element that's tied to your IV? Similar story. We have an instruction called compact, which essentially just compresses all the active elements inside of a vector, moves it down. In x86, this is VP compress. And then you just return the bottom element. So these 2 cases are quite common. For instance, they're essentially STD find and hash map, for instance. This will get us to optimize those codes further. This does trigger an issue that's becoming more and more of an issue for us. The reload has some issue with its heuristics during coloring. And so in this case, it thinks that Z31 is live after this instruction here. And so it makes a copy of it. This copy is completely unneeded, and in most cases, it just costs us 2 cycles. There is a work in progress patch, but the problem is getting the heuristic correct across different architectures is quite hard. The last part is doing early breaks without an epilogue when stores are visible. Stores are harder because we have to copy the store. So at the moment, to make early break factorization correct, we have to move the store into the loop latch, because we can only execute side effects when we know the entire iteration has completed. However, if you take an early exit, we must perform the side effects for the partial iterations before the value for the exit. So to do that, we have to duplicate the stores and then use the same mask partitioning instruction as before. This is problematic because we can't just add a new store to the scalar code. So instead, we're changing the vectorizer to materialize the stores in the right basic blocks, but no longer move them in the scalar code. This also allows us to get epilogue factorization back, because at the moment, we move the scalar code before factorization, but when doing so, it breaks the UIDs of the basic block. And so when doing epilogue factorization, we can no longer tell which store this pointed to. That's why today we don't have epilogues for early break. And that's what I just mentioned. With that change, we now get epilogues back. The next part, and probably one of the biggest things for next year, is to teach the vectorizer to be able to refactorize already vectorized code. With the idea is that you have a lot of code written with like intrinsics, but they were written on older microarchitecture, or the code itself was not very efficient. So we've been teaching the vectorizer that if you have a vector element, that's just another lane, but the lane contains X number of elements. This representation is then also able to combine vector code and scalar code, and if it needs to, it unrolls the scalar code to fill the remaining vectors. But essentially, for instance, this loop on the right, on the left, is loading 8 bytes at a time, and it can then, the vectorizer can then refactorize it to 16 bytes at a time, and then generate an epilogue if it needs to. Or, for instance, if you switch on SGE, it's able to transition between ISA versions. In order to support that, ARM has a new extension called HVLA, Hybrid Vector Length Agnostic. I think so. Essentially, what it does is it makes it easier to make this transformation from a fixed 128-bit SIMD system to a VLA one by introducing operations that operate on quad-word elements at a time. So then each single element here is a full vector in your old code. So this this makes it easier for the vectorizer to refactorize neon code that already uses all the full pipeline, the full vector width. The instructions are mostly around load stores, permutes, and reductions, because your old code might have been reducing within the 128-bit vector ranges. So the idea is to treat this in the vectorizer as just another vectorization strategy and not something special. The next part is dealing with vector initialization. We are getting very good at vectorizing, but we are very bad at initializing vectors. So a lot of times we get messages from people working on codecs and stuff that they have these constants that they're using to create a particular mask and stuff like that, and the compiler makes a complete mess out of it. So for instance, in this case, the one above here, you're essentially loading values sequentially. The C code might look difficult, but it's essentially just loading things sequentially. However, in Gimple, what we end up doing is we end up creating a constructor that has one of the elements, and then we have a sequence of bit field inserts. This means the backend has absolutely no chance to optimize it. The change in forward prop is to push the elements directly into the vector constructor to give the backend a chance. So for instance, the first one here, we notice that it's a linear load. So you go from needing 4 loads to make this result into a single one. It also breaks, so in this case, these loads here can't execute until the load and replicate runs. So the second one is just much quicker. It's also able to realize patterns. SLP can SLP memory loads. So by pushing the values in, SLP is now able to tell you that your values are just repeating in a particular pattern, and then give it to the backend, which is able to do a load and replicate. So I have this patch working today. However, I'm deferring it into 16 because it's quite disruptive to backends. As soon as it's in, everyone's vector construction will become much worse because no one was expecting them to actually see in the constructor itself the different arguments. So it's a bit late in stage 1, so I figured I'll defer it until early next year. The other issue we have is that AArch64 has these instructions to do load and replicate of memory accesses. but their addressing modes are different than your normal loads. And unfortunately, at expand time, we legitimize addresses. So we then make it so that you cannot use these load and replicate instructions anymore. So you end up here with needing a load and then a duplicate. So the idea here is to teach expand that if you have a vector with a memory operand, try to expand it directly first, and only if you fail, go force it to a register, and then try again. Now, for advanced SIMD, we have the issue where for early breaks, sometimes advanced SIMD code is better because it has better throughputs on compares, etc. However, compares and advanced SIMD don't set flags. So we have to do this little reduction sequence here to get to the end, which is quite wasteful. Now, if you have SVE enabled, we can essentially just mask off the first 128 elements, do the compares, and then use the SVE comparison instead of advanced SIMD. This is nice, however, you can only do so if you know that the values that you have incoming are actually Boolean values. In the mid-end, we have a vector Boolean mode. In the back-end, they're all just integer modes. And so we can never tell what the original lanes look like. So you can't really use combine or whatever to do this. So instead, what we do is we do the rewriting now in expand. So in expand, we'll go out and figure out if you have a sequence of compares on masks, and then we deprecate C branch on vectors, and we introduce new optabs, C branch any and C branch all, that give the backend context of what you're trying to compare and what part of the CC flags you're interested in. And this allows you to do whatever you want with the comparison, including in our case, change it to SV. Then we also want to do, for SVE at the moment, we generate a compare and then a p-test. Now, a p-test instruction, what it does is it resets the flags based on the sizes of the predicate elements. Now, if the sizes of the elements are the same, the p-test is completely useless because the CC flags end up being the same. But for differing sizes, the values for the first and the last flags change. So whether the first element is active or the last one is active. However, for early break, all we really care about is whether any lane is active or no lanes are active. So it means the p-test is completely superfluous. However, in RTL, we can't tell this context anymore because every instruction just tells you which flags it sets, and the other one just tells you which flags it consumes. So we have to do this early on. So again, this is done in expand. We rewrite it to C branch any, and then this instruction is able to tell them to expand immediately in a sequence that doesn't use the intermediate CC flags. In order for this to work, however, it relies on being able to CSC likewise compares. The problem is that at the moment the backend, the mid-end does not have an operation for a masked compare. Masked compares are created by doing a normal compare, and then you do a bitwise AND with a mask on the result. This doesn't work because this mask is pushed in to the compare way after the last CSC pass. So to fix that, we have new optabs for masked compares. Now, as I mentioned before, SVE compares, they set flags. So remember what I mentioned before, that we have a sequence of compares and we do ORs in between to reduce them to a final value. For SVE, we really don't want this because compares are usually single throughput. So you created a very slow comparison there. However, instead, what you want to do instead of the ORs is you want to branch immediately after each compare. Because they already tell you whether you have an element or not. Once you support this, we can also support AND blocks. At the moment, the vectorizer can only support ORs, but we need to be able to support ANDs as well. For instance, this is the hot loop in Zalang in Spec 2017. There are two ways you can handle this. Again, you can use short circuiting. So in the SVE case, if we know we're not going to AND the block, skip the block entirely. Don't conditionally execute it. For ISAs that don't have this flexibility, we will then execute the block and then do a conditional select at the end to merge them together. The other thing we're working on is that SVE has this instruction that does a n times m matching. So essentially, think about std find if. You give it a range of predicates, and this instruction can compress the predicate back into one instruction. So you can check, for instance, in one instruction whether any value you've loaded in your vector register contains X, B, 7, or C. And it'll give you an index of where. So it allows us to remove this chain of ORs and compare it to a single instruction. We also want to be able to generate code for switches in general. At the moment, if convert has a switch lowering passed inside of it, but it's quite limited. It can only handle the case where the return here is invariant. It can't handle nested switches. It can't handle switches with ranges inside of it. So it's really quite limited. So our proposal is to, instead of extending that, move the code entirely into the vectorizer. Because the vectorizer is able to pick how to resolve this issue. Whether you want to collapse the switches into one, for instance, if you don't have any short circuiting, this is beneficial. Or to keep them separate if you can short circuit and jump over the blocks. So at the moment, we have a patch upstream for this, undergoing discussion. Also, since we've gotten to the point where we can vectorize a lot of loads now with early access inside of it, a lot more loops are being vectorized that shouldn't have been vectorized with early break at all. So for instance, this one, the loop is just adding a cap on the maximum number of iterations. So this shouldn't have gotten to the vectorizer the way it did. So instead, what we do now is in IV canon, we've added optimizations that, for instance, for these kinds of loops, we'll change the loop bounds here to say it's going to be iterate to a minimum of n and 1,000. And that then gives you the second code gen here, which is a lot smaller than the ones for faster. The next major piece of work we're working on that we're still hoping to get in today. So today, the vectorizer needs at least one exit to be counted. It doesn't care which exit is counted, it just needs one. However, what we want to be able to support is completely uncountable exits. So in this case here, for instance, you generally have no idea how much you're going to iterate. But you do know that at some point you will stop, probably. So we've extended the vectorizer to not need scav information to be able to vectorize. Of course, this introduces problems like costing and alias analysis, and stuff like that we're trying to work through still. But the code you generate out is something like this. You basically just have only vector comparisons as your exit condition. And, right?
The vectorizer needs trip count information, right? Okay.
Yeah. So at the moment, we essentially, the vectorizer is now able to generate code by just, so this is essentially an extension of early break. We say your main exit is always true, and then your alternative exit is the while condition here. And so that's why here at the end, this is your, this would allow you to break out this one, but if not, you just loop endlessly.
Go, thanks.
There is one restriction that you have in place, is that you must have at least one file node in there. Something must iterate, otherwise it's a completely infinite loop. We're also working on basic block SLP for VLA. So at the moment, we only support SLPing of fixed vector lengths, but you also want to be able to do variable vector lengths. At the moment, we do it by saying each block can be a maximum of 128 bits, because that's the minimum vector size of SV. And then you just predicate out the elements and create a block from that. So here, for instance, you can do the addition by predicating out 3 elements and then doing the vector load, addition, and store. That part will feed then into being able to do basic block SLPing of early break. So essentially, you start discovery at a file node, and you keep moving up. The big problem here is that our current SLP discovery is a bit weak already on normal cons expression. So for instance, we don't vectorize this second bit at all either. However, Clang is able to make a nice SLP log out of it. Yeah, so the other thing that we have is that at the moment, the way the vectorizers determines the vectorization factor is kind of the reverse of where we want it to be. So here, because your induction value is an integer, but you are loading data from along, the vectorizer will go, okay, so then the vector mode I want for the induction variable is a V4SI. So then it means I need to unroll the loop to get 2 vector loads of the longs. This is kind of backwards because the induction value shouldn't really influence the vectorization, the way we vectorize. So we end up unrolling this loop needlessly. And so we have to kind of invert this. I think Richie tried before and failed, but I think we have to try again. So that you fix it, or tell it that forced life inductions don't count towards your vectorization factor. One of these two. But at the moment, this is what forces us to unroll code, which would have been profitable had we not unroll it. The last part is teaching the vectorizer to support loops with many pointers. So there are compilers today, certain proprietary compilers, that will vectorize this code using a bit of a clever hack. They will dump all the pointers into an array. They will do a quicksort on the arrays, so they'll dump the start and end pointers, do a quicksort, and then they do a linear scan comparing the start and the end pointers of the next element. And if none of them overlap, then you know that none of them alias.
You would be calling the library routine for this, right? Sorting.
Yeah, for a quicksort.
So self-contained programs like kernels will have an issue with this, right?
Yeah, I mean, you could definitely disable it. But the biggest issue for us is that we don't want to keep performing it every time you call the function. And so the idea is that maybe we can use IPA to create a specialized version of a function that that if you call it from this point, the points are aligned.
So how would you decide whether we have to do the sorting here based on number of pointers, right?
Yeah.
So is there a minimum cut that you have for deciding that?
I genuinely know this. At the moment, we have a bug report upstream where we're trying to figure out what's the best way forward. But it does seem to happen. There are real programs out there with a lot of pointers coming in. And so we need some way to still be able to vectorize it.
And there can be one pointer with a different range of accesses as well, right?
Yeah.
Say A goes from 1 to N, then again A accesses from P to
Exactly.
Z or something. What would be your min and max there?
So if you have the same pointer with different accesses, you think you would dump into the array multiple entries. So because it stores the start and the end. So for each of them, you would have to add the offsets.
Okay.
And I think that's it.
So I have a question on dispatch scheduling. I haven't looked at the patch yet, but is it written generically or so you have set of dispatch rules, right, for the dispatch scheduling?
Oh, yes. So the dispatch scheduling, right?
Yes.
Yeah. So the dispatch scheduling we have at the moment today is only looking at SV. So essentially, it breaks down the instruction per pipelines that they use. And then we basically just have a model of how many instructions each pipeline can take before it's full.
Is it integrated into the scheduler or is it?
It is part of the scheduler, yes. So it's an existing thing in GCC. At the moment, only the x86 backend uses it, but it's been there for ages.
Okay.
It has to be an either or, right? Basically, we have to go with dispatch scheduling or the latency or throughput-based scheduler, right? Both cannot operate at the same time because one is at front end and another is the back end, right?
Correct. So when I say throughput-based scheduling here, it's mostly in the vectorizer.
Okay.
So and the dispatch scheduling is later in RTL. Because in the vectorizer, we do have to know throughputs in order to choose between the different ISAs.
Right.
I've got a question about the vector initialization changes.
Yeah.
I think if you do that and the vector actually contains pointers, I'm not sure if that's something you're focusing on, then you might get additional runtime relocations. Because if you're loading the initializer from memory because you now have a proper initializer constructed, then that has to be relocated by the dynamic linker. Whereas when you create it piecewise via different separate instructions, then you might be able to use PC relative addressing to construct the values, and then you don't get the relocation.
Yeah, it doesn't unconditionally rewrite it, right? So the backend needs to still accept it, and you can reject it based on whether it's comes from your base pointer or stack or whatever. The only thing that's unconditional is the forcing into the vec constructor itself, if it's a bit filter ref, and if it's a bit filter ref, that value itself isn't a load. So that one won't access memory.
Yeah, for building glibc, we would like to avoid generating runtime allocations for static or hidden data because it creates bootstrapping issues for the dynamic linker. And so we will, even if we might want to build the dynamic linker with vectorization enabled, obviously, but yeah, then we have to turn off this particular feature. And we currently see architectures that generally do not use relocations for hidden or static data, suddenly getting relocations because of things getting built out, getting initialized in memory using dynamic relocations and then loaded into a vector register. Just something that we would like to be able to turn off.
Yeah, I'll need to take a look at a couple of examples to fully understand it. But yeah, no, we can definitely tweak around it.